Assalamu alaikum wa rahmatullahi wa barakatuh. In this video, we're going to solve an application for part 3 of chapter 4, Mechanical Oscillations. Please prepare the notes that you have taken in the preceding parts to use them when you need to. The question says, a horizontal elastic pendulum is made up of a solid of mass m equals to 100 grams, which is 0.2 kilograms, a spring R of negligible mass and stiffness K equals to 20 newtons per meter. The center of mass of S can move smoothly on horizontal rail along the x' or x-axis, which is taken as the gravitational potential energy reference level. At t0 equals to 0, S is launched from O with an initial speed v0 vector equals to minus v0I vector, where v0 is positive. So S oscillates on the x' or x-axis with a proper angular frequency omega 0. The abscissa of G at t is x, and the algebraic value of v is dx by dt. The first part, write at any time t the expression of the mechanical energy of the system S, R, Earth in terms of m, k, x, and v. Please, every time we ask you a question, pause the video and think of it. The mechanical energy is the sum of the kinetic potential energy, the gravitational potential energy, and the elastic potential energy. But the gravitational potential energy reference level passes through the center of mass of the solid S. So, the potential energy gravitational is 0, thus the mechanical energy is just half mv squared plus half kx squared. The second part, establish the differential equation in x that governs the motion of the pendulum. You know that we have two methods to find the differential equation, either using Newton's second law or the conservation of mechanical energy. Here, because the first question was about the mechanical energy, so we're going to use the conservation of mechanical energy. The mechanical energy is given in the previous part as half m v squared plus half kx squared, but we know that there is no non-conservative forces, thus the mechanical energy is constant. This means that the derivative of the mechanical energy is 0. So let's derive the mechanical energy, keeping in our mind that the derivative of v squared is 2v v prime, where the derivative of x squared is 2x x prime, and v prime is x double prime, where x prime we can replace it by v. Then take v common and divide by half in the two sides of this equation. We get v into mx double prime plus kx, where v in our case is not 0. We can say that x double prime plus k over mx equals to 0, and it's the second order differential equation. Part 3. The solution to the differential equation is given by minus xm sine omega 0 t. Determine the proper angular frequency omega 0 in terms of k and m. How can we benefit from this equation? We can find its derivative, which is minus omega 0, where omega 0 is the derivative of omega 0 t. Then we make the second derivative, where here we can write minus omega 0, xm is still the same. Derivative of cosine omega 0 is minus omega 0, the derivative of omega 0 t, times sine omega 0 t. Then we can write it as xm omega 0 squared sine omega 0 t, and now we can replace it in the second order differential equation. Now replace x double prime by this answer, xm omega 0 squared sine omega 0 t. Then replace x by what they gave us, minus xm sine omega 0 t equals to 0. Take xm sine omega 0 t common, then we can write it as xm sine omega 0 t into omega 0 squared minus k over m. This one is not 0, it's a time equation, then we can say omega 0 squared minus k over m equals to 0, thus omega 0 squared equals K over M, and omega 0 is radical K over M. Part 4. Deduce the value of the proper period T0. We know that omega 0 equals to radical K over M, and we're going to deduce the period from this expression. How? We know that T0 equals to 2 pi over omega 0, and 1 over omega 0 is radical M over K, so just replace it in the expression. Now replace M and K by their values. The answer is 2 pi over 10 seconds. The last part, determine the expression of the amplitude xm in terms of V0, K, and M. At T0, we said that x prime equals to minus V0. Then let's write the expression of x prime, which is minus xm omega 0 cosine omega 0 t, which is found before in a previous part. Let's replace t equals to 0 in this equation. Then we will have minus V0 equals to minus xm omega 0 cosine 0, where cosine 0 is 1. Then we can write it as V0 equals xm radical K over M. Then xm is V0 radical M over K. This is the end of the application of part 3. Please try to solve it again by yourself. Thank you for watching.